Okay, well, if we talked about velocity being the derivative of position, velocity is dx dt, and acceleration is the derivative of velocity, dv dt, then by fundamental theorem of calculus, we should be able to go back up through integration. And indeed you can. So, if we have velocity, we can define that as, let's write it this way, v naught plus the integral from t1 to t2, or ti to tf, initial and final, or 0 to t. Let's write 0 to t. 0 to t of the acceleration dt. So in order to go back up, you have to be given initial conditions, of course, to get a full answer. But this is definitely the truth. And position, likewise, if you are given initial position, you can find it from a velocity function by taking the integral from 0 to t of your velocity dt. Right? So if you're given some function as a function like v is a function of t, vt is equal to yada yada yada, you can integrate it and get position if you're given the initial position. If you're only given velocity, you're not given anything about initial position, it doesn't tell you anything about where you are. You can find out where you are relative to where you started, but you have no idea where you are. If I say you're going 15 miles an hour, it doesn't tell you where. It could be on Mars, it could be in Europe, it could be here in Flagstaff. So you have to be given initial conditions to be able to solve fully when going back up this way. Okay, so we're going to do one example here and then call it good on this. Oops. So set this back to where I want it. All right. Grab this guy. All right. And then throw the example up there. You read. All right. Sally is driving along a straight highway in her 1965 Mustang. Well, guess what? It's not Sally anymore. It's Joel. Because your instructor had a 65 Mustang. It just so happens this is me in 2007 washing my 65 Mustang. Look at that. So we'll put that nice over there. Nice picture there. All right. So Joel is driving along a straight highway in his 1965 Mustang. At time equals 0, when she is moving at 10 meters per second. So that's V naught. V naught is 10 meters per second. Excellent. We have an initial condition. In the positive x direction, she passes a signpost at x equals 50 meters. Her x acceleration, that is initial x position as well. So at time equals 0, she passes a signpost at x at 0. Time equals 0 is equal to 50 meters. Our x acceleration as a function of time is given here. So we have, we have this here. I won't rewrite it. You can see it, hopefully. Find her x velocity, v sub x and position as a function of time. So we're going to integrate this guy, yeah? So given what we said earlier, we have acceleration, and we just need to integrate it to find v. We have our v naught, right? So it's going to be equal to v naught plus the integral from 0 to t of a dt. A dt. I'll just write this out here one more time there. That's what we're solving for. And so what that actually is 10 meters per second plus the integral from 0 to t, yeah, as a function of time. So we're going for the function. Is equal to, well, here, let's do this. Is equal to 2.0 meters per second squared minus 0.10 meters per second cubed times t. So the cubed seconds here is a little weird, but it's going to get canceled out with the t, right? So we're going to get back to meters per second squared, and this is a function for acceleration. And if we integrate this, if you remember, right, of x d, let's see, x m dx is equal to 1 over m plus 1 x to the m plus 1, right? Very quick review. And so what we get is that our function v of t is equal to 10 meters per second plus 2.0 meters per second squared times t minus 1/2 0.10 meters per second cubed t cubed. T squared rather. T squared. There we go. So there it is. That is our function for velocity as a function of time. We were only able to figure it all out because we were given that initial velocity. And it also is wanting to find her x position, her position x as a function of time. So then we integrate it again. So x is equal to x naught plus the integral from 0 to t of v dt, right? That's our formula. X naught was 50 meters, so which is equal to 50 meters plus the integral from 0 to t of this whole function. So we got to put this all in here. 10 meters per second plus 2.0 meters per second squared times t minus 1/2 0.10 meters per second cubed t squared. I didn't close my brackets earlier, nor do dt. Let's fix that just like that. There we go. Okay, so back here, we now take the integral. So this is going to be equal to 50 meters. It's going to be x as a function of time. 50 meters plus 10 meters per second t plus 1/2 2.0 meters per second squared t squared minus 1/4 0.10 meters per second cubed. Oops, not fourth, sixth. Just, 3 times 2, 6 cubed. There it is. So we've found the functions. So that's just basic calculus. If you've already taken calculus, that comes as no surprise. But it's useful to bring it into physics and do what we can with it. All right, so that ends chapter 2. And I encourage you to do as many problems as you can possibly stuff into your day between now and watching the next lecture. You obviously will have some homework assigned, but the more problems you do, the easier it will make your life. So the amount of time that you spend doing problems and reading the chapter and going through all this stuff, you will be spending more time, but your effort, so to speak, will be going down because things will get easier. You will magically find yourself more capable the more you do this stuff. So I really encourage you to just do some extra problems if you have the time. Okay, see you in the next lecture.